the magnetic dipole moment. In physics, we like to identify the main features of a problem, ignoring details that do not matter. In this period, we describe the current carrying loop by a single vector mu, its magnetic dipole moment. We take the direction of the mu to be that of the normal vector n to the plane of the coil. We define the magnetic of mu as mu equal to NIA. N is the turn number. I is the current in one turn. So Ni, we put it together, is total I, IA. Is magnitude. And direction is the direction of A. So we write this mu, the magnetic dipole moment of a carrying current is IAN, IA. Okay. And the torque, as we learned in previous section, equal to IA cross B, the magnetic field acting on the current carrying loop. This A is the area times N. So this we call mu. So the torque becomes mu cross B. It's very easy to remember. Okay, they call it magnetic dipole for a current carrying loop. This is very similar to the torque equal to P cross E. Remember the electric dipole. In the electric E, it will be exert a torque. Why an external magnetic field is exerting a torque on the magnetic dipole, such as current carrying coil, works must be done to change the orientation of the dipole. The magnetic dipole must then have a magnetic potential energy that depends on the dipole's orientation in the field. For electric dipole, we have shown that U theta of the electric dipole in electric field is minus P dot E. In a strict analog, we can write for the magnetic case that magnetic potential energy equal to minus mu dot B. Now, when this mu is parallel to the B, this dot maximum you have minus is the lowest energy. From energy conservation point of view, it's more stable. Okay, more stable. Okay, yeah. And in this case, the potential energy of the magnetic dipole is the lowest. This is minus. That's biggest. Okay, yeah. And when theta is 90 degrees, this is mu. This is B. Okay, okay. We put the N is parallel to B but opposite direction, and we put this potential is minus mu B cosine 180. Cosine 180 is minus 1. Minus 1 minus 1 is positive. It's the largest, the lowest. Okay. A magnetic dipole has the lowest energy when its dipole moment mu is lined up with the magnetic field, like this case. Okay. And it has its highest energy when mu points in the direction opposite to the Y. The difference in energy between these two orientations is the potential difference. Okay, from 0 to 180, we put this together, you get a 2 mu B. This much work must be done by an external agent, something other than the magnetic field, like the heat excitation, to turn the magnetic dipole so 180 degrees, starting when the dipole is lined up with the magnetic field. Our Earth, a proton, an electron, and the simple bar magnet are also magnetic dipoles. We'll look at some magnetic dipoles. Okay, see the Earth, very huge. and a small bar magnet 5. Okay. An electron have electron dipole 9.3 times 10 to the minus 4. And a proton is 1.4 10 to the minus 26. Sample. Figure shows a circular coil with 250 turns and an area A of 2.52 times 10 to the minus 4 square meter and the current 100 milliampere. The coil is at rest in a uniform magnetic field of magnet B equals 0.85 Tesla. With its magnetic dipole moment mu initially aligned with B. Question A. In the figure, what is the direction of the current in the coil? Now, because mu is here, so the current direction must be this one by right hand rule, right? Question B. How much work would the torque applied by an external agent have to do on the coil to rotate it 90 degrees from its initial orientation, so that mu is perpendicular to B and the coil is again at rest? That's because no kinetic energy, because again at rest. So we will find, okay, mu theta is minus b dot b, and the work applied should be 90 degree minus 0 degree. Remember, in this case, no kinetic energy. No kinetic. Okay. So we put this number inside. We get it mu b. Now we put a number inside. Mu equal to I and AB. Number, okay, I is the given is 100 microampere. We should use the ampere as a unit. Okay, and the area is square meter, and B is Tesla. We get this one.